The talk I'm going to give now is essentially mainly the work by Viktor Saverkin, whom you can see here. He will also present a poster. So if you want to discuss things in more detail, you can of course either come to the breakout room after this talk, or you can discuss with Viktor at his poster. I'm inclined to say in the afternoon, in a few hours. From my perspective, it would be in the afternoon. Anyway, today we are going to talk about Gaussian moment neural networks. This is essentially one particular descriptor and how we can use that to provide transferable and uniformly accurate interatomic potentials. This is not the only area of machine learning that my group works in. So today's talk will be centered around potential energy surfaces, essentially. But we also use, for example, Gaussian process regression that we have heard in the last talk by Markus Reyer in geometry optimization. So really to provide the training set and increase the training set on the fly during a geometry optimization course in order to find minima, transition states, reaction paths, whatnot. Yes, and we've also done some work in implementing force training in the ANET code in a collaboration with Nong Atris, and who will be talking tomorrow, I think, and Alex Urban. So let's get into what I'm going to tell you today. I will first cover Gaussian moments, which is one particular descriptor, one way of transforming Cartesian coordinates into an input for machine learning techniques. Michele Gerardi has given a nice introduction in what descriptors are, so I can essentially skip the first quarter of my talk. Then I will tell you a bit about the implementation, details on how one can make such a code actually very fast and very efficient. In order not to have too many data, or not to need too many data from which to learn, active learning strategies and learning on the fly is becoming more and more important, which is not particularly trivial, especially for neural networks. We will talk about details there. And then I will talk about applications, and those applications I picked out are mainly one example from astrochemistry and one example where we go beyond learning potential energy surfaces, in the words of Michele. So essentially we're learning magnetic anisotropy tensors. Right. This is essentially the slide I could skip already. What is a descriptor? It is a coordinate transformation from Cartesian coordinates in order to something that a machine learning model can understand. I mean, Michele has given a very nice overview about that. I will say a few words again from my perspective, but it's essentially very similar to what Michele has pointed out already. So the requirements for such a descriptor are that it should be local or atom-based. It should be scalable, essentially. We want to have one descriptor, and with that, we want to be able to describe larger and larger systems that can be condensed phase, that can be larger molecules, whatever. So therefore, for many properties, an atom-centered description, a local descriptor, is beneficial because that can be extended it can be extended, and the computational effort will grow linear with the system size. Of course, fundamental invariances, fundamental properties of our molecules should be encoded into the descriptor directly. And many of those, or important ones of those, are of course translation, rotation, and exchange of like atoms. The model could in principle learn these quantities, but it's supposedly more efficient if we put them into the descriptor. At least this is the physics point of view. I've talked to computer scientists and they challenge that view actually. So machine learning experts from computer science would always take the data-based approach, so that the machine learning model should also be able to learn those. But in that sense, I am more on the physics side, I must admit. We want to have analytic energy gradients, maybe not only gradients, but also Hessians. So the potential energy surface, the descriptor should be smooth in order to be able to take derivatives. It should be systematically improvable. We want to have one knob, one thing that we can turn in order to make the descriptor maybe more expensive, but also more accurate, and then less accurate and faster. Yes, it should be fast overall. An efficient implementation is important. It should be data efficient, as few energies as possible, because as we have discussed just now, calculating the energies is so expensive that everything else is not all that important, which is not totally true. Sometimes the learning also takes some time, and it should be numerically stable. This is overall important. Now, I mean, Michele has written a nice review about that. Many approaches are available in the literature. I think they more or less started out with the work by Bela Parinello, these symmetry functions. The closest descriptor to ours that showed up in the literature, I would say, Alex Shapeyev's moment tensor potentials given here. what we are doing in Gaussian moments is essentially we want to describe the environment of one atom. So essentially the atomic environment of one atom. We want to have a descriptor that tells the neural network or the machine learning algorithm in general which atoms are in the vicinity of my particular atom. Now the radial distribution is easy to do. We set up basis functions and expand the expand the environment into a radial basis. This is easy to do. We pick Gaussian basis functions for the radial basis, but essentially many other possibilities are suitable there. Doesn't really make a difference. We pick out Gaussian basis functions plus a smooth cutoff function in order to provide smooth potential energy surfaces in the end. The angular distribution is more interesting, and there is a bit of variation available in the literature. What we do is essentially as a quantum chemist, I like to see it as the discrete equivalent to a expansion into spherical harmonics. So we have an S-like function if we just add the number 1 for each atom within the cutoff sphere. We're only taking care about angles now. The radii are already taken care of. We have P-like functions by summing up the unit vectors to each of the atoms within our cutoff sphere. We can create D-like functions, and this is always a discrete function. You know, it's not really a D orbital. It's something D-like or the angular momentum-like. We can create D-like functions by summing up the tensor product of 2 such unit vectors. And then, of course, higher orders, F-like, G-like functions by higher order tensor products. Of course, that provides a scalar. This is easy. That provides a vector, which is not as useful for an input into machine learning models. And that would provide a tensor, which is also not all that useful. Additionally, these vectors and tensors transform equivariantly with our molecule, so they will rotate with our molecule. But essentially, we want to have something that is invariant with respect to rotation, and that can be easily solved by tensor contractions. So essentially, we contract all of these combinations of tensors that will result in scalar properties, and these resulting scalar properties, this can be done by diagrams in a nicely way to be nicely overviewed. These scalar properties are used as descriptors. They are put into our machine learning algorithms. Now, from what we are doing now, this can be used for any kind of machine learning algorithms, neural network, Gaussian processes, linear regressions, whatever you want to do. We use it with neural networks, and therefore we call this thing Gaussian moment neural networks. This is a typo here. So essentially, our Gaussian moments are coupled with neural networks, and that's a difference to Alex Chapeev's work, who uses linear interpolation as machine learning model, if you want. We use one neural network for all atom types. Now, so of course, the neural network knows if this is a carbon or a nitrogen atom, but essentially this one neural network for all atom types leads to the effect that a carbon atom can learn from a nitrogen atom or a hydrogen atom or vice versa as well. It distinguishes it, but the atom types can still learn from each other, and we found that beneficial. We will train on atomic energy. We do train on atomic energies and forces. In our implementation in TensorFlow, these training on gradients essentially can easily be implemented by automated differentiation. So this is easy to do. Since this is implemented in TensorFlow, we are very efficient on CPUs, GPUs, and whatever other new processor types that may come up. So from a computational science point of view, the code is really efficient. To do molecular dynamics, we have interfaces to the ASE environment and to LAMPS for doing production simulation for our fitted potential energy surfaces. And the data we generate by essentially any quantum chemistry code. Mostly in our case, it's MolPro and TurboMol, but we have interface to ChemShell and therefore interface to essentially any quantum chemistry code for the input data. But input data are easy to transform anyway, it's energies and gradients. Our code is available open source at this URL. I will give that later on as well. Right. Now a bit to technical things. So this is probably the most technical slide that I will show today. We use a fully connected feed-forward neural network with 2 hidden layers. Nothing special about that. I think everyone uses that in our potential energy surface community if you want. the training is improved by the normalization of the feature vectors of the descriptors. These shift and scale parameters for the normalization of atomic energies and forces, we made them trainable. That makes it actually more efficient in the overall setting to have these shift and scale parameters trainable. And then a significant improvement in the quality of the training as well as the training speed was achieved by using neural tangent kernel parameterization, NTK parameterization, which leads to a balanced training of all layers and of all nodes within the layers. So that essentially all of them get the same force, the same gradient in the training, and are trained on a similar scale, so to say. That makes the training more efficient. Now, why do we put in so much effort into the training speed? As we have seen already, I mean, calculating energies and forces, calculating the labels takes a lot of CPU time. However, if we want to do active learning, if we want to do automated generation of potential energy surface, and then we need active learning, then we have to retrain quite a lot. And then it does really make sense to spend some time and effort into fast training, because this will then really automate the creation of potential energy surfaces and other properties to train as well. So first, a few words to the capabilities. So what can our code actually achieve? The descriptor is systematically improvable. That means if we use a larger descriptor, if we use more Gaussian moments, we get more accurate in a power law, essentially. So it is really nicely, smoothly improvable. We can really have one knob how many Gaussian moments we use, and that will result in the error in the prediction. This is the force error here, but it will look similar for the predicted energy error. We can have a look at learning curves, and they also look normal, let's say. So the larger the training set, the smaller the error gets. We do not see any saturation as long as we use a sufficiently large number of Gaussian moments. We can compare to other methods that are available in the literature, and it compares quite nicely. There are approaches that are more accurate, but in that specific case, this is a few things that we picked up, of course, to compare. There are others as well, but among those that we picked out, essentially that FCHL 18 is more accurate than ours, but it's also somewhat inefficient. It is a large kernel method, which requires more CPU time to train. Now, the CPU time and timing is always difficult to compare to. I mean, we made quite an effort to write a fast code, but the only thing I want you to learn from this slide is essentially that our code can compete with the other codes concerning the timing. The individual numbers are probably not all that relevant. What I want to say is our code is fast. These are numbers from the literature, and they will have been done on different computers, on different CPU types, GPU types. So therefore, it's not 100% comparable. And the same is for inference. Of course, we have also spent quite some time to make the inference fast and efficient, because in the end, we want to have something that, well, it won't compete with force fields, with very nicely parameterized force fields, but it still should be fast in order to provide fast sampling. Right. So essentially, our code is reasonably efficient, and that is necessary for active learning. Because if we want to do active learning, as I said, we have to retrain over and over again. And that can only be done essentially if the learning and the training is efficient and is done nicely and fast. To do active learning, we need some kind of uncertainty estimate. Now, that is a graph that you have seen just now in Marco's talk. Essentially, that means for any machine learned model, we have training data. They might have an uncertainty. We have a predicted mean value, or some predicted value essentially, and then we can have an uncertainty estimate for the uncertainty of the prediction. Now, such an uncertainty estimate is trivial and directly provided by Gaussian process regression. It's also easy for linear interpolation, which is probably the reason why Alex Chapeyev used linear interpolation for his moment tensor potentials. For neural networks, to provide an uncertainty estimate is by far not as trivial. There are approaches in the literature, so one can use Bayesian neural networks, one can do ensembling, query by committee, so a few neural networks and averaging them. There's Monte Carlo dropout. There are a few approaches for these two at least. For all of them, essentially, one needs to recalculate a neural network a number of times, which is moderately efficient. What we did is we applied one method of statistical learning theory, essentially, so optimal experimental design, to the last layer weights of a neural network. That results in a Bayesian uncertainty estimate, so also in a statistical uncertainty estimate for the predictions, for the uncertainty of the predictions, which is reasonably consistent with the actual observed errors. Now, that is the main ingredient for active learning. We have an uncertainty estimate for our prediction. And now this is essentially everything we need for active learning. What we do is we train a model on some input data. Then we sample structures. The sampling can either be done directly on the machine learned potential energy surface or initially probably on some other cheap potential energy surface in order to create input structures. Sampling, MD sampling is one possibility, but of course, depending on the property you want to learn, other techniques might be necessary as well. From these samples, we select structures, input structures, molecular geometries, which show a high uncertainty in the model that we have, in our potential energy surface that we have at the moment. High uncertainty means that the model will get a lot of information from including these structures. Now, that can be done at the moment directly. In the end, we want to do batch active learning, so pick a number of structures, include them in the model, and then we also have to find out essentially how different are these new structures. Are all of them correlated? And the goal is to pick as uncorrelated structures as possible. This is something that we are still working on. Then we calculate labels. This means in practice atomic energies and forces. We update the training set, we retrain, and in such an iteration, we can improve the potential energy surface significantly. What kind of improvement can we actually achieve? So this is again for the QM9 dataset. The reference for the dataset has been given on the previous slide. For error measures that count, that essentially focus on the smaller errors, we do not get any improvement. So if we look at the maximum MAE, the maximum average error, absolute error, sorry, this essentially weights smaller errors larger. There's not much improvement between random selection, which would be the open dots, and our active learning solution would be the full dots. RMSE, which weights larger errors larger, so the squared of the error essentially. There we already see an improvement by our active learning. Especially for larger training set sizes, of course, where the active learning really kicks in. But if we focus on the maximum error, so the largest error within the test set, which is of course independent of the training set, we see really an improvement by the active learning. And that means by active learning, we obtain globally uniformly accurate global potential energy surface. That means energy surface that are accurate everywhere. We reduce the largest error on in the area of configuration space that we are interested in, and therefore improve the potential energy surface overall. Right. That brings me to applications. The first thing I want to show is really only a test run, which was, I mean, we don't gain any new physics here. This was a titanium oxide data set. We didn't create a data set ourselves. This was taken by the publication of Nong and Alex. PBE calculations with a cutoff of 6.5. This is essentially only the only input parameter that we have to choose in our neural network model, the cutoff. Everything else is one standard parameter for the number of Gaussian moments, but this is really, it can be tuned, but it's not necessary to tune. We have trained the model on 3 low pressure phases of the titanium oxide, anatase, rutile, and bruchite, and then predicted the high pressure phases, columbite and badellitite. And we can see that for one of these phases, for columbite, we find the minimum at pretty much the correct cell volume, at the correct lattice parameter, and also the energy is predicted very well. The crosses here are the DFT reference data. For the other high pressure phase, the minimum localization, so the cell volume is predicted very well as well. The energy is somewhat off. But these are, of course, data that the system has never seen. So both of these phases are really new phases that the system has never seen in training. So even extrapolation works to some degree, as usual in machine learning. Now, something else where we used machine learning quite a lot is astrochemistry. I have been working in astrochemistry quite a bit, especially because a bit like Michele, I did atom tunnelings and nuclear quantum effects in the past, and I'm still very interested in those. And that brought me into the area of astrochemistry, essentially. We are interested in the formation of molecules on icy surfaces, and ice may be water ice, CO ice, mixtures of those, whatever. And something that is experimentally very difficult to access is surface reactions like adsorption versus desorption versus bouncing versus diffusion, and all that require molecular dynamics sampling. And this is really something where neural network potential energy surfaces can help. What we looked at are nitrogen atoms on a water surface, which is important for astrochemical models, for kinetic models essentially, but it's very difficult to get experimental data on that. So this is something where we included training. As training data, we used small clusters at different temperatures, higher temperatures to cover the high energy areas, but also low temperature, of course, and the interaction with nitrogen atoms. Yeah, these are the technical data. A lot of sampling structures. We used active learning in the end on that data set. The data set itself is published as well, but here I actually want to come to the results, things that we have found out. We ran thousands of trajectories of nitrogen impinging on the ice surface at different angles, at different energies, at different surface temperatures, and so on. The outcomes are sticking probabilities. How likely will it be that our nitrogen atom actually stays on the surface? This is one trajectory where it in the end stayed on the surface. And these sticking probabilities, depending on the incoming energy, are something that people need in astrochemical models. And that's something we can provide. A different thing that we calculated with the same data set is really the diffusion of nitrogen atoms on the water ice. There you can't see anything diffusing anymore because we got rid of all the dynamics by doing metadynamics and calculated a free energy surface of nitrogen diffusing on a round model of an ice surface. And then on that free energy surface, we identified minima and transition states and did kinetic Monte Carlo for the whole thing. And that resulted in temperature-dependent diffusion constants, which is also something that will be quite interesting for the astrochemistry community. Well, that is as much as I want to say about astrochemistry. There's one small thing that I want to mention, and this is my last slide with scientific content, namely the learning of something else than potential energy surfaces. Here we learn the magnetic anisotropy tensor, or also called D-tensor. This is important for single molecule magnets. Molecules like that, where we have a metal, in this case a cobalt, in the center, and this has a large magnetic moment and can in principle be used for qubits, for spintronics, for all kinds of interesting applications. What people want to know there is the lifetime of these magnetic excitations, essentially. So how long can a qubit store its information? The D-tensor that we learn is essentially the parametrization of the zero field splitting Hamiltonian. Spin times D-tensor times spin is the Hamiltonian. The properties are, it is a symmetric, traceless, atom-specific tensor. So we have one tensor, not for the whole molecule, no global quantity, but one tensor for the cobalt atom. In principle, we're only interested in one atom. It's equivariant with the molecule. So the whole tensor rotates and translates with the molecule. The translation is trivial, this is no problem, but the rotation with the molecule is tricky. We decided again for a physics-based approach rather than a data science approach. So we constructed a learning scheme where the result will be equivariant with the molecule, will be symmetric and traceless. And to do so, we train an auxiliary quantity, a scalar quantity for each atom. That sounds familiar, doesn't it? I mean, it's the same as we train potential energy surfaces. There we also have a single quantity and energy per atom. And from that single quantity, from that scalar quantity, we construct symmetric traceless tensors. And we do that in the same way as quadrupole moments would be constructed. And these tensors are the things we compare with the training data, and then based on those, we can make predictions. The training data come from STI calculations, spin orbit contributions. These are done by Andreas Köhn. And we can see that essentially we can train all those quantities, all those components of this 3x3 rank 2 tensor quite nicely and quite accurately. Well, that's essentially everything I want to tell you. Let me summarize. I hope I have convinced you that this Gaussian moment neural network approach is an efficient descriptor for molecular structures, for potential energy surfaces, but other things as well. The tensors have, of course, also been trained by the Gaussian moment neural networks. For active learning, we need an uncertainty estimate, but we can provide that as well, and we need fast training. But having that, we can really calculate globally accurate potential energy surface, which leads to robust and transferable potentials. This is the result of the proper training, so to say. And I've shown you applications to solid state structures as an example, surface astrochemistry and magnetic properties. Our code is available at the URL given here. And as a final slide, I want to thank the people who have actually done the work. This is a picture of my group as we meet at the moment. Sometimes we can meet in person as well already. Most of the work here has been done by Viktor Saverkin, who will show a poster in a couple of hours. It's poster P01. There's also within the conference Daniel Born, who has the poster P04, who works on Gaussian processes of geometry optimization. And the astrochemistry was done by Hermann Molper-Theres in our group. I should announce that we may have will have a PhD position available starting beginning of next year at some point. And with that, I want to thank the funding agencies for all the money they gave and you for your attention. Thank you.